What happens from when we power on a microcontroller until we reach the main function? Normally, when we run a C program on a microcontroller, we assume that the program starts at the main function. After all, that's the first function we implement and where the debugger drops us. But that's not where the program truly begins. So what actually happens when a microcontroller starts? Someone experienced might say, it depends. It depends on the microcontroller hardware, the tool chain, and the other software components involved. And while it's true that it depends, there are also some generic startup steps common to most microcontrollers, and by studying one of them, we can still get some understanding of the general startup process. So in this video, we're going to study an example, specifically the startup code that ST provides for one of their STM32s. Then, once we've looked at that, we will implement our own version of it from scratch. And the best way to explore an example is by picking up the ID and toolchain from the manufacturer for a specific microcontroller, create the basic project, and then use a debugger to step through the instructions before the main function. The STM32 microcontroller on my desk, which we will use as an example in this video, is based on an ARM Cortex-M processor, like all other STM32s. Not only is this one of the most widely used processors these days, but it also serves as a good platform for exploring startup code. ST provides CubeID as their officially supported ID for STM32s. In this first part, we will use this ID to create and build a simple project, mainly to generate the default project files, including the startup files. But after that, we'll switch to VS Code for the rest of the video. Let's create a simple project. And finding the part number of my board. That's the one. Next. Fill in a project name, next, and then finish. As seen, even for this minimal project, ST already provides several files to get us started. Then building the project. And after building it, we also have an executable we can debug, so now we can jump over to VS Code. Here I've opened the same folder to the project we just created. And to flash and debug this, we can create a debug configuration in launch.json. We will use the Cortex debug extension, and we need to modify a few things in here. First, the executable field, so it matches the path to the executable that CubeID produced. Then we can add a few more lines below to use OpenOCG and GDB for flashing and debugging. That's it. This microcontroller board includes an onboard debugger, so it's just a matter of plugging in the USB cable and pressing the play button in VS Code to flash and debug the program. And voila, we end up at the main function and can step through our C program as usual. Someone else has taken care of the startup for us and our C program just works. And that's why we normally don't need to worry about what happens before we get to main. But in this video we want to understand what happens, so let's try to get the debugger to stop at the first CPU instruction instead. And to do that we can modify our debug configuration again, replacing the option run to enter point with break after reset. And then launch the debugger again. When the debugger stops at the first CPU instruction on the microcontroller, we usually find ourselves in a file called startup something, often written in assembly because some low-level tasks can't be done in C, and at this point the C runtime has not been set up yet. If you're not familiar with assembly, this file can be a bit tedious to go through, but stay with me, we will breeze through it and then later use C to write our own startup code. But before we get to this point, that is, before we are about to execute the first CPU instruction, there are things that have happened in the hardware already. For example, the voltages have stabilized, clock signals have synchronized, peripherals and registers have been reset to their default states, and so on. Things have happened that we have no control over. And we are not going to dig into these things in this video, and instead focus on the things we have control over. But there are two hardware steps we should know about. First, most processors start executing from a fixed memory location. At startup, the program counter register is initialized with the reset vector, the pointer to the first instruction the CPU will execute, the one we are about to step over. On ARM, this reset vector is loaded from the second entry in the interrupt vector table. Second, the stack pointer register is loaded in a similar way, with its address stored in the first entry in the interrupt vector table. Automatically loading the stack pointer in hardware like this, however, is not typical across all architectures. It's more of a bonus feature specific to ARM processors. In other architectures, it instead has to be manually initialized with the CPU instruction. This is one of the reasons it's nice to write startup code for ARM. To confirm this, we can scroll down and look at the interrupt vector table in the startup file from SD. The first value is the address to the stack, and the second value is the address to the reset handler. By the way, the interrupt vector table itself is placed at the beginning of the flash memory, which is specified by the linker script that SD also has provided. Quite a lengthy one, we won't get into it, but we'll write a simple linker script later, so for now just know that it exists. Let's instead go back to the startup file again and step through the reset handler. The first instructions here set the stack pointer register, but as I just pointed out, ARM is kind enough to do this for us in hardware, so this has no effect. We can see this by inspecting the stack pointer register. Its value remains the same when we now step over the move instruction. I don't know why these instructions are here. Perhaps SD kept them for consistency with other startup files or something. The next instructions are specific to the STM32 microcontroller and applies when booting from the system memory, including the internal bootloader, which can be selected via the boot pins. It does this by checking if the reset vector address starts with hex 1F, but since we boot from flash memory, the reset vector address starts with hex 80, and this compares to false and then branches ahead and skips the instructions that follow. After this, it's time to initialize the C runtime environment. While the previous steps were more specific to the particular microcontroller, C runtime initialization, often referred to as C runtime 0, involves general steps required for any C program to behave correctly according to the C standard. Setting up the C runtime environment can be complex, but here SD does the bare minimum, which basically is to just initialize the variables stored in RAM, because at power on, RAM contains undefined values. First, they initialize the data section, the memory section where the initialized global and static variables are stored. These variables have their initial values in flash memory, and these must be copied to RAM during startup so that they can be read and modified during runtime. After initializing the data section, they zero initialize the BSS section, the memory section where we store uninitialized or zero initialized global and static variables. This ensures that these variables are correctly set to 0 at runtime. Next, they call system init, a function intended for certain low-level hardware initialization, such as configuring clocks, peripherals, or working around chip bugs. In startup code for other microcontrollers, I've seen this placed earlier, before the C runtime initialization, which makes sense because some MCUs may require hardware like memory to be set up before initializing the C runtime. In this case, the function is empty, but SD suggests that clocks can be configured here. Then they call a function libc init array, which primary purpose is to call the constructor functions. While constructors are mainly a concept in C++ and not part of the C standard, some compilers like GCC supports them through an extension where a function can be made into a constructor function by marking it with an attribute constructor. libc init array itself is a function provided by the runtime code that comes with the standard C library implementation Newlib. We can't step into this function and see the source code because it hasn't been compiled with debug flags, but later in our own code we'll define a constructor function and at least see that it works. Once the C runtime is initialized, we are ready to jump to main, and then we are back to where we normally seem to begin and can step through as before. Even though we should never return from main in a freestanding environment like a bare metal microcontroller, for good practice there is an endless while loop here to catch us in case we accidentally do. Overall, the goal of the startup code is to take the microcontroller from a reset state, where there are a few guarantees about the initial conditions, to a functional C environment with everything initialized as expected. Now that we are more familiar with this process, we are going to discard the startup code we just looked at and write our own from scratch. We will target the same microcontroller, but we will not build the code with CubeIDE, but instead download the ARM GNU toolchain. CubeIDE wraps SD's own build of this toolchain, so this shouldn't be too different, but it allows us to play with the toolchain more directly. Then I've created an empty project and transferred the launch configuration. We just need to modify the path to the executable here again. To start with, we can create a bare minimum C file with the main function that returns 0. Then to compile it, we can run GCC with a couple of flags. First the target CPU, Cortex M0, then indicate thumb instruction mode, what C standard to use, enable debug symbols and disable optimization, and add -C to just compile. That's it. There are some other flags we normally want to use as well, but let's keep it simple for this exercise. By the way, in this video I'll write out all the compile commands directly on the command line like this, which is a bit tedious, but I want to avoid using a build system and clearly show each step. With that, we get an object file, which contains machine code that hasn't been linked yet. We can disassemble it using object dump, another tool from the toolchain. Simple as expected, use the instructions for entering and exiting the main function. Only 12 bytes in size. Then we can link it to produce an executable that can be flashed onto the microcontroller. But now we start running into problems, because even if we have just provided a single object file, GCC will link in some other components by default, things that will interfere when we want to experiment with our own startup code. So we are going to discard them, but before we do, let's first understand what it's trying to link in. One thing it's trying to link in is Newlib, an implementation of the standard C library, which in turn depends on a set of system calls to be implemented. This is why we get the linker error. In the CubeIDE project we looked at earlier, ST actually implemented these system calls in a separate file, which is why we didn't encounter the error there. To bypass the linker error, we can provide empty stubs for these system calls using the nosys.specs flag. This isn't a solution, but it allows us to link the program and inspect the resulting executable further. If we look at the size of this executable, we can see that it linked in a lot of stuff, a whopping 1700 bytes in the text section and over 1000 bytes in the data section. And looking at the disassembly with object dump again, there are many functions besides the main function we provided. Some of these are from the standard library, like memset. Others come from the runtime library code or startfiles provided with Newlib, which is another set of object files that GCC links with by default. Finally, we can see that the addresses of the instructions for these functions are placed an order of magnitude away from the flash memory address of this microcontroller, which starts at hex 8 million. The reason for this is that without a specified linker script, GCC uses a default one that isn't tailored for this microcontroller. We can dump this linker script by adding the -verbose option to the linker flags. A complex linker script, but here we can at least see where the address hex 8000 is coming from. Overall, the default behavior of GCC that we are seeing here is more suited for hosted environments, where an operating system handles part of the startup, including a loader program that loads the C program into memory. For our exercise with a freestanding environment, we want to eliminate this behavior. The standard C library and the start files are useful, and we will reconsider adding them back at the end of this video. We can discard the standard library using the libc flag. In that case we can also remove specs nosys. And by the way, we can see all of the object files we are linking with in the verbose linker output. Here for example is the static build of Newlib. And after linking with libc, the static build of Newlib is now gone from the list. We do get a linker error though, because we are still linking with the start files, which depends on code from the library we just removed. We can remove the start files in a similar way using the flag no_startfiles. Then all CRT related object files also disappear. The only thing left is a static build of libgcc, which contains runtime support for GCC. However, it won't get used in our case, so we can leave it be. We do get a warning though, because we're still linking with the default linker script, so let's remove it and replace it with an empty one, creating a new linker script file and adding it to the command with -t. Then the verbose output just shows our empty linker script. If we now also disassemble the executable, we can see that nothing has been added to it compared to the original myprogram object file. It's still 12 bytes, so now we finally have a clean slate to start from. From this clean slate, we need to begin by writing the first code the CPU will execute. As mentioned before, after power reset, as part of the hardwired initialization, the ARM Cortex-M0 loads the program counter and stack pointer registers with the first two values of the interrupt vector table, the table that starts at hex 8 million in this case. In other words, we should load the PC register with the address of the first function we want our microcontroller to execute, and the SB register with the address of the stack. We can begin by creating the startup file, which we will write entirely in C. In this file we will define the first function to run. ST calls this function reset handler. We will call it ISR reset, since it behaves like an interrupt function that triggers on a reset. For now, it will simply call the main function and then while loop. We will also need an external declaration for main to tell the linker it's defined in another file. While we're at it, we should also define an interrupt handler for hard faults, as it's easy to trigger one by mistake when working with startup code, a simple while loop to catch us. Next, we can define the interrupt vector table, which is a table of addresses to interrupt functions, including the ones we just defined. To make the code more readable, we can typedef an interrupt function and then define a table as an array of this new type. According to the datasheet, the table contains 48 addresses on this microcontroller. As mentioned, the first element should be the address of the stack's starting location. We can add an external symbol for that here, assign it in the interrupt vector table, and then define its address in the linker script shortly. The next location is the address of the first function to run, which in our case is ISR reset. Then is the location for non-maskable interrupt, which we can leave as 0. And after that, it's the location for the hard fault handler. That's it. We could also add a bunch of weak default handlers, which is generally good practice, but let's keep it simple for this exercise and instead leave it as a comment. We're going to place this table at the start of flash memory in the linker script, and to do that we need to give it a section name, which we can assign with an attribute. We also need to set used to prevent the compiler from optimizing it away. Next, let's move on to the linker script. It's still empty, and we won't add much to it since linker syntax is a topic on its own, but we need to define the memory layout of our microcontroller, which includes specifying the memory regions, where they start and how big they are. According to the datasheet, the flash memory starts at hex 8 million and is 32 kilobytes, while RAM starts at hex 20 million and is 6 kilobytes. Then we can add the stack symbol. The stack is typically placed at the end of RAM and grows downwards. We'll use the same symbol that we declared in our startup file. We also have to define the memory sections that hold our code and data. By convention, the linker places code in a section called .text. On ARM, the start address of the text section must be aligned on a 4-byte boundary. We'll place .text at the start of flash memory and place the interrupt vector table at the beginning of this section. The keyword keep so that the linker doesn't discard it. After that, we can use asterisk syntax to place any section from any object file with a name that begins with .text here. Basically all the code. For convenience, we can mark the end with another symbol and ensure it's aligned on 4 bytes. We can now compile and link our startup file with our program using the linker script. We don't need to recompile myprogram.c since we haven't made any changes to it. Oops, now we got a compile error because I forgot the space, so let's just fix that. And then compile the startup file again, and after that relink the executable. And by looking at the disassembly, we can verify that things are placed as expected. The IVT is at hex 8 million, the start of flash memory, and it contains hex 2,1800. That's the stack pointer. Hex 1800 is 6000 in decimal, so 6 kilobytes. So that's the end of RAM. And then hex 8 million CD, which is the address of ISR reset. Or well, the last bit differs because it's used to indicate thumb instruction mode. Then is the address for the non-maskable interrupt handler, which we set to 0. And lastly, the address for ISR hard fault, which, like ISR reset, has the last bit set to indicate thumb mode. In other words, the disassembly appears to be correct. So let's also flash and debug it. Yes, we end up at start of ISR reset, and the program counter register contains the address of ISR reset. And the stack pointer register contains the address of the end of RAM, so they are both loaded correctly. And stepping through the code, we reach the main function. At this point, it may seem like our C program is already working, but it's not. We haven't initialized the C runtime environment, which means our C program won't fully behave as expected. We are missing crucial steps both in the startup file and the linker script. We can see this more clearly if we expand our program a bit. Here I've added some arbitrary variables with different scopes and storage classes. If the program behaves according to the C standard, they should sum to 60 and we should end up in this while loop. Let's rebuild, link, and debug to see what happens. Starting from the beginning and stepping through main. Stepping, good so far. But here we trigger a hard fault. So we end up in our ISR hard fault function. Let's start over and look at the address where it happens. This is a store instruction. It's where we write the sum value to the sum variable. Register 2 holds the sum value and register 3 holds the address of the sum variable. In this case, R2 contains 58, not quite 60. But more importantly, the address of the sum variable is hex 8,130, which is a flash memory address and not a RAM address, which explains where we are hitting a hard fault. We are not allowed to write to flash with the store instruction. The compiler has generated instructions assuming these variables are placed in RAM by the linker. The problem is that we haven't instructed the linker to place them in RAM yet, so it's placing them in flash memory. This works fine as long as we are just reading them, at least for the data variables, but not when we try to modify them. We can see this in the disassembly as well. The global and static local variables are part of the data section. They have been placed at hex 1,120. While the uninitialized variables we expect to be initialized to 0 are part of BSS and placed at hex 8,128. By the way, the reason the sum was 58 and not 60 is because the BSS section is not flashed, so those memory locations have all their bits set to 1, which interpreted as signed int is -1. To fix this, we have to update the linker script to instruct the linker to place the data and BSS section in RAM. We can add them in a similar manner as the text section, a line on 4 bytes, but then instead of flash we place them in RAM. For the data section we also need to tell the linker with the add keyword to copy the initial values from flash, and we should add a symbol to reference the initial values. The BSS section is similar, but these values should just be 0 initialized, so no need to store any initial values in flash memory. Link again. And looking at the disassembly, the data and BSS section are now placed in RAM. Data at hex 20 million and BSS at hex 20,000,008. Let's debug again to see if the hard fault is gone. Stepping. Yes, no hard fault this time. But the sum value is still wrong, even more wrong than before. So this evaluates to false and we return from the main function and end up here instead. This is because in addition to placing the variables correctly in RAM, we must also initialize them before reaching main, as RAM contains garbage values at power on. To achieve this, we need to perform the same runtime initialization we saw in the startup file from SD before, which we should do in our startup file as well. For data section, it's a matter of copying the initial values from flash to RAM, referring to the symbols we just defined in the linker script. 2 pointers, one pointing to the initial values in flash memory, the iData symbol, and another pointing to the destination address in RAM. Then we can simply loop over and assign all variables. Note we can write this in C, but we must be careful. As we just saw, we can't fully trust our C program yet, meaning we shouldn't make use of static or global variables, nor should we call any external functions or code that relies on a proper C runtime environment. Clearing the BSS section is even simpler. Just loop through all the values in the section and set them to 0. And then we can call these functions in ISR reset before calling main. Then compiling the startup file, linking and debugging this again. Stepping through from the beginning, first we initialize the data variables, then we clear the BSS variables. Stepping further, now the sum contains the expected value, the condition evaluates to true, and we end up in the while loop. Our C program behaves as expected. Strictly speaking, we have now set up the bare minimum required for a C program to run on a microcontroller. It turns out not that much is needed, but there are a few more things we can add for a more useful C program. One thing we can do is to link the standard C library again, the library we removed earlier, to make typical standard functions available to us. We can add it back by removing the Newlib flag and specifying the specs flags to provide the naked system call stubs. We should also add nano.specs for a smaller version of Newlib aimed at embedded systems, and the CPU and the thumb flags to link with the correct variant of the library. Once again, to make full use of Newlib, we should not use nosys.specs and instead implement the system calls ourselves, but that's not for this video. With this, we can for example use standard functions like memcopy. We can first build without the standard C library to see that we get a linker error from memcopy. And then if we build with it, the linker error is gone. Moreover, like SD did in their startup file, we can call libc init array to support construct functions. not so much for our own sake, because it's a feature you rarely use in C, but code you depend on like external libraries might, and if not implemented, may lead to subtle issues due to improper initialization. libc init array is defined in the runtime code for Newlib, and we can call it just before main, and add an external declaration to tell the linker that it's implemented in another file just like the main function. Then compiling and linking, we encounter a linker error. The way libc init array has been compiled, it expects to call a function _init, which is normally provided by the runtime files from Newlib, specifically the object file crti. But since we don't link with those object files due to the no startfiles flag, we can get around this by defining an empty stub for this function instead. Compiling and linking yet again. No linker error, but we must also add a section to the linker script where the addresses to the constructor functions can be placed. GCC expects a section called init array for this purpose, and symbols init array start and init array end, marking the start and end of this array. To verify that it works, we can add a constructor function in our program and see if it's placed in the init array section and if it's called before main. Compiling and linking again. Looking at the disassembly, our constructor function starts at this address, and scrolling down to init array start, we can see that that's the value it also contains. Remember, the last bit differs because it's set to indicate thumb mode. Flashing and debugging. Stepping. Once again, we can't see the source code for libc init array because it was not compiled with debug symbols, but stepping through, we can see that it first calls _init, and then eventually our constructor function. So it works. Now we got the startup file comparable to the one SD provided. We will add no more, but let me comment two more possibilities. First, we could do additional hardware initialization, such as configuring clocks or writing to specific registers to work around bugs mentioned in the errata. It's common to have a function system init for this, like we saw in SD startup code. Second, for a more feature-rich C runtime, we could consider linking with the C runtime start files from Newlib again. Then we would remove the no start files flag and replace the calls to libc init array and main with a call to _start. The C runtime 0 from Newlib includes features like semi-hosting, profiling, transactional memory, function hooks, and more. While these are not required, they can be useful in certain cases. Keep in mind though, this will likely require some additions to the linker script as well. Yes, there are more things we can add, but we have covered the most important bits now, and this should have given you an introduction to Microcontroller Startup, enough to explore and understand this on your own. In this video we are focused on a specific microcontroller, and I want to emphasize again that startup code will vary depending on the microcontroller hardware, the toolchain, and the other software components involved. The programming language also matters. We focused on C because it's the most common, but a language like C++, for example, would require more startup code, while something like pure assembly would probably need less. Either way, understanding the example in this video will make it easier to grasp others. Finally, a question that still might linger is if we should care about this at all. The truth is, in everyday development, we typically don't need to bother with what happens when a microcontroller starts, because someone else handles it for us. But if curiosity isn't reason enough, there are actually times when it's helpful to be familiar with it. Like when a crash occurs before main, or when you have to perform tasks early in the boot process. However, if you do need to modify the startup code, be careful, as it's easy to introduce subtle bugs. So understand how it works, but maybe avoid changing it unless you really need to.